Synthesized analog hi-hats are pretty fascinating. That's because emulating any kind of cymbal using an analog circuit is tough, since the sound a real cymbal produces is not quite pure noise, but also not really harmonic. Still, a couple classic drum machines like the Roland TR-606 and 808 took their best shot at it, with quite strange sounding results that I personally really like. So I decided to follow suit and came up with this simple but very versatile and crunchy sounding hi-hat circuit. To understand how it works, we'll start by identifying the different functional blocks that make up a classic analog hi-hat. First up, some sort of noise source. There are designs that go for simple white noise here, but I think this sounds a little basic and overly artificial. That's because, as I said before, real cymbals produce a sound that's sorta halfway between pure noise and something faintly harmonic. To get there, I took inspiration from Roland's implementation, which uses a very dissonant swarm of square wave oscillators to produce vaguely metallic-sounding noise. Next, we'll have to set up a filter to get rid of frequencies that real cymbal noise doesn't contain. Also, we'll want to emphasize some of the remaining frequencies to make the sound more sharp and biting. So the filter will need to be resonant. Since the harmonic content added by a resonant filter is usually not very complex, we'll then want to route our signal through some sort of distortion to add more crunch and metallic sheen. After that, we'll have to shape the result into a quick burst, or a somewhat longer one, depending on whether the hi-hat should currently be open or closed. For that, we'll use an amplifier, which we'll control using an envelope generator. Finally, we'll apply another round of high-pass filtering to get rid of any remaining low end in the signal. This sounds pretty good to me, so let's try to implement it in an actual circuit. We'll start by creating our noise source. For that, we'll need a quick and efficient way to set up a swarm of square wave oscillators. Our best bet here is probably a Schmidt trigger inverter-based solution, since it consists of just 3 parts per oscillator: the inverter, a capacitor, and a resistor. If you've seen my DIY VCO series, you'll mostly understand how this works. Still, here's a quick recap. When we first flip the power switch, the capacitor will be empty and the voltage above it will be 0. The Schmidt trigger inverter will interpret this as a low input state, causing it to put its output into the high state. Now, current flows from the chip's output through the resistor and into the capacitor, filling it up. As it fills up, the voltage above it rises. At some point, it will cross the Schmidt trigger inverter's upper input threshold, causing it to latch into the high input state. In response, it'll put its output into the low state. Because the capacitor voltage is now much higher than the inverter's output voltage, current will flow out of the cap and back into the output. Until we hit the lower input threshold, the inverter latches into the low input state, and the whole process repeats. At the inverter's output, this gives us a square wave whose frequency depends on the size of both resistor and capacitor. Increasing either will decrease the frequency, because it takes longer to charge and drain the cap. Knowing this, we can use a 4106 chip, which houses 6 individual Schmidt trigger inverters to set up 6 oscillators tuned to 6 different dissonant pitches. Okay, but what pitches are we going to use exactly? Well, to make our lives a little easier, we can simply adapt the values that Roland used in their TR-606 hi-hat. In ascending order, they tuned their 6 oscillators to approximately 245, 306, 365, 415, 437, and 619 Hz respectively. Since I want to get something more chunky than the very high-pitched 606 hats, I'm going to shift all of those frequencies down by around 50%. Next, we'll need to pick capacitor and resistor values that give us these resulting frequencies. Circuit simulators come in really handy here. With those values settled, all that's left is mashing the 6 oscillators together. For this, we can go the lazy route and simply use 6 100K resistors to create a passive mixer. To try this out, I've already set everything up on the breadboard. As you can hear, the result is a dissonant atonal swarm of bees, just as expected. But it doesn't really sound like a cymbal yet. One problem is the low end, but the high end is also a little too intense. To deal with it, we'll set up a filter that removes both low and high end frequencies at once. For that, we'll chain a simple passive high pass and a simple passive low pass together. If you need a refresher on how these work, I've got an entire video explaining passive filters. Link is in the description. Now, by selecting the right capacitor and resistor values, we can carve out the rough frequency band that is suitable for hi-hats. Using a smaller resistor or capacitor in the high pass will eliminate more of the low end, while using a bigger resistor or capacitor in the low pass will kill more of the high end. When playing around with this, I settled on a 1 nanofarad capacitor combined with a 10K resistor for the high pass and a 2.2 nanofarads capacitor plus an 82K resistor for the low pass, which gives us a frequency spectrum at the output that looks something like this: a cut at around 400 Hz and a gentle drop starting at around 10 kHz. That's pretty close to what Roland used for their 808 and 606 hi-hats. I just decided to cut out a little bit more of the low end, since our mixed oscillators are more bottom-heavy overall. And here's what it sounds and looks like if we route our oscillators through the bandpass. To be able to gauge the frequency range better, I've replaced my oscilloscope with a spectrum analyzer. As expected, the sound loses a lot of its low end, and the harsh overtones are tamed a little bit. At the same time, we also lose a lot of volume. I had to really crank my audio interface's input level. That's the unfortunate side effect of passive filtering. To fix it, we'll turn our passive bandpass into an active bandpass using an op-amp. To save a couple extra components, and more crucially, to be able to add resonance later, we'll go for an inverting configuration here. It works like this. First, we ground the op-amp's non-inverting input. Then, we take our high pass and we connect it to the inverting input. This might look a little bit confusing because we previously picked up the filter's output from after the capacitor, not the resistor. But in an inverting op-amp setup like this, the inverting input acts as something we call a virtual ground node, meaning that it stays at or very close to 0 volts during operation, while also reading the input that will be amplified. So for our filter, it doubles as the connection to ground for the resistor and the output node for the filtered signal. Next, we take our low pass and put it into the op-amp's feedback path. Again, this setup might look a little confusing because in the passive version, we applied the input signal to the resistor, while we connected the capacitor to ground and picked up the output from above it. Here, since the inverting input doubles as a ground node and the filter's input, both the capacitor and resistor are connected to it. Finally, we've got to link the low-pass output to the op-amp's output. which completes the feedback path and allows the op-amp to push and pull current through both filtering stages. Okay, but how does this increase the output volume of our bandpass? That's the tricky part about this setup. Since the op-amp does everything it can to keep its inverting input very close to 0 volts, the impedances of both filter stages, that is, how hard it is to move current through them, matter. If the impedance before the inverting input is low, but the impedance between that input and the op-amp's output is high, a small change in the input signal requires a big change in voltage at the op-amp's output to keep the inverting input close to 0 volts. So the gain we apply to the filtered signal depends on the relation between the input impedance and the feedback impedance. Conveniently, with our chosen component values, that input impedance is about 3 times lower than the feedback impedance, meaning that we'll get an output signal that's about 3 times louder than the one we get from the passive version. And here's how this pans out on the breadboard. To avoid clipping the signal, I had to turn down the input volume, so the amplification is working as expected. Great. Next, I'd like to add some resonance to make the sound more sharp and biting. To get there, we only need to add 2 components, a capacitor and a resistor. If we insert them into the feedback path like this, then our filter will strongly emphasize the low-pass stage's cutoff frequency. If you've watched my previous video, in which we built a kick drum circuit, you'll recognize this structure as a bridged T topology. In that video, I explained the mechanics behind this in detail, but here's the basic gist. Whenever the voltage at the inverting input changes, the op-amp will try to neutralize that change by adjusting its output voltage. Previously, that process was very straightforward, because all the op-amp had to do was charge or discharge the single capacitor in the feedback path. Now, with the added cap and the resistance to ground between the two, things get pretty complicated, since both caps need to be charged and discharged, but they do so at very different speeds, and they're interacting with one another in the process. As a result, the op-amp over and undershoots its target repeatedly as it struggles to stabilize the voltage at its inverting input. And the resulting oscillation that is added on top of the input signal is a perfect sine wave swinging at the low-pass stage's cutoff frequency. Which, to make things even more complicated, also depends on the resistance going to ground between the two caps. That relation, at least, is simple. The lower the resistance, the higher the cutoff frequency. If we replace the single 2.2 nanofarad capacitor we used previously with 2 3.3 nanofarad capacitors and combine them with a 470 ohm resistor to ground, we should get a resonant peak at around 7 kHz. And since it would be nice to add some manual control for the tone here, we'll insert a 1K potentiometer between the resistor and ground. This should allow us to move the cutoff from 7 kHz all the way down to 4 kHz. And here's how this sounds in practice. You can see the huge peak in the spectrum analyzer. And indeed, it does sound much more sharp and aggressive. Cool. With the filtering and resonance sorted, I'd now like to add some crunch to our processed signal. And while we could use a dedicated distortion stage for this, there's a way more efficient solution. In Roland's 808 and 606 cymbal and hi-hat sections, they used something they dubbed the swing-type VCA to modulate the signal's volume. That VCA is so crude and bare bones that it adds a ton of distortion as a byproduct, which would be horrible for any other application, but in this case, it's essentially killing 2 birds with 1 stone: volume modulation and distortion in a single efficient little block. So let's take this block apart. The central piece is a simple NPN transistor, set up as a high-gain amplifier. For that, we combine a big 33K collector resistor with a very small 100 ohms emitter resistor. We'll ignore the diode for now. Then we bias our input using a capacitor followed by a big 1 megaohm resistor connecting the transistor's base to the positive rail. This ensures that current is flowing through the transistor even if the signal is idling at ground level. That current can then be manipulated by the signal pushing against or pulling at the capacitor. The transistor in turn replicates those changes in voltage at its collector, though with a huge gain. That huge gain is the key to the distortion added by the VCA. Basically, any tiny change in voltage at the input results in a big change in voltage at the collector. So any signal that's not extremely low in volume will be transformed into a harsh, distorted pulse wave. That pulse wave's amplitude, and that's the kicker, is then determined by the control voltage we apply to the 33K resistor, simply because it sets the maximum voltage that we can get below that resistor when the transistor is fully closed. So by lowering the control voltage, we lower the volume of our output signal. Alright, but what about the diode between the 33K resistor and the collector? Well, there's one small issue with this setup. If the control voltage is 0 and there's no diode here, current will flow into the base, out of the collector, and towards that low voltage node. And as the input signal oscillates, so will that current flow, resulting in an audible signal at the VCA's output. By putting the diode there, we stop that from happening, and our VCA will be perfectly silent at 0 volts control voltage. To test this, I'll first apply a constant 5 volt signal to the control voltage input. This way, we'll be able to clearly hear the distortion added by the VCA. This doesn't sound too great. We just get some very thin crackling. What's up with that? Well, the issue is that our signal is just too loud going into the VCA. This means that our transistor is mostly stuck in its fully on or fully off state, also called saturation and cutoff, with the occasional super quick transition, resulting in the thin crackle we just heard. To fix it, we'll simply lower the volume of our oscillator mix. Right now, that mix is an almost 12 volts peak-to-peak signal, which is very loud. So let's insert a small 680 ohms resistor to ground after the passive mixer to scale that down to just about 400 millivolts peak-to-peak. And yeah, that sounds a lot better. Next, let's try to vary that control voltage to verify that we can modulate the output volume that way. And as expected, we get complete silence at the minimum CV setting. Great. There's just one small thing that bothers me, though. The super high fizz introduced by the distortion is a little too intense for my taste. To fix it, we'll simply add a small 2.2 nanofarads capacitor going to ground from the transistor's collector. In combination with the 33K collector resistor, this will act like a very gentle low-pass filter, taming the high end a little bit. To make the effect more noticeable, I'll again apply a constant control voltage to the VCA. And yeah, that sounds a lot more mellow and rounded. You can adjust the intensity of this effect by choosing a smaller or bigger capacitor. So that's the VCA and distortion blocks down. Next up, we'll want to add a snappy envelope generator to drive our VCA and give us a quick percussive hi-hat hit. For that, we can reuse the design I came up with for my kick drum circuit. The basic version of that design consists of just 5 components: a diode, a capacitor, a potentiometer, a resistor, and an NPN transistor. It works like this. If we apply a short voltage pulse, also called a trigger, to the diode, the capacitor is filled up instantly and then slowly drained through the resistance to ground. This creates a gradually falling voltage curve whose steepness only depends on the resistance we dial in using the potentiometer, since we're isolating the controlled discharging process from the rest of the circuit by setting the transistor up as a buffer. If we then connect the transistor to our VCA, we should get the percussive hit we were looking for. There's just one thing missing to be able to test this: a trigger. For that, we can again reuse something from my kick drum design, the gate-to-trigger converter. This little circuit takes in a gate signal from a sequencer or an LFO and transforms it into a super short voltage pulse. For that, it combines a high-pass filter with an op-amp-based comparator. That high-pass transforms the gate into a quickly falling voltage curve, and the comparator then heavily distorts that curve into a pulse. To be able to adjust the trigger's size, we then route it through a little PNP transistor-based limiting circuit. It works like this. If we don't apply a voltage to the transistor's base, no current can flow through it, and the 12-volt pulse is divided down to around 5 volts by these two resistances. Conversely, if we do apply a voltage to the base, then that transistor will pass exactly enough current to cap the trigger's size at that voltage, giving us voltage control over the hi-hat's accent level. Great. To test this, let's start out without any accent CV applied. By playing around with the envelope's decay potentiometer, I can influence the length of the hi-hat hit. Now, if we combine this with a CV sequence applied to the accent CV input, we can already get some interesting results. Still, our hi-hat is sounding a little too chunky for my taste. And that's because our VCA didn't just add a little fizzy distortion, but also plenty of low end. So let's add another high-pass filter to complete our signal chain. We'll start off with a simple active high-pass filter, which we get by buffering a passive high-pass using an op-amp. If we combine a 1 nanofarad cap with a 47K resistor, we get a cutoff frequency of about 3.4 kHz, which should get rid of most of the chunkiness. The buffer then ensures that the output voltage stays the same by keeping the output impedance low. And here's how this sounds in practice. As expected, the result is a little less chunky. Still, I feel like we could do better. Our current filter is what we call a single-stage high-pass, which means that it has a 3 decibels per octave roll-off. This is pretty mellow, so a lot of frequency content below the cutoff point makes it into the output. To make this slope more steep, we can simply add another high-pass stage with the same component values. This way, we get a second-order high-pass filter, which should have a steeper 6 decibels per octave roll-off, while keeping the cutoff frequency the same. To see the effect this has more clearly, I'll feed our VCA a static 5 volts control voltage again. And yeah, that does get rid of the low end more effectively. So let's hear how this sounds using our envelope again. It's not terrible, but it could honestly use a bit more bite. To fix this, we'll simply make our high-pass filter resonant. That way, we emphasize the frequencies around the cutoff point, which should hopefully give us a little more of that metallic ringing. Alright, but how do we make this setup resonant? Easy. We just have to connect the first 47K resistor to the op-amp's output. In this way, we introduce positive feedback to the system, because the filter's output is routed back into the first filter stage. This destabilizes the filter's operation, leading to the same over- and undershooting behavior we saw previously in our resonant bandpass. We call this setup a Sallen key filter, by the way. One caveat though. Since our op-amp currently has a gain of 1, since we set it up as a straight buffer, the amount of resonance added will be pretty minimal. To push it a little, we just have to increase the gain by putting a voltage divider into the op-amp's feedback path. With a 100K 100K divider, we bump that gain to a factor of 2, which should be plenty. To test this, I'll first apply a constant control voltage to the VCA. As expected, we get a pretty pronounced bump in the 3 to 4 kHz range. And here's how it sounds when I drive it using the envelope again. That sounds pretty nice and metallic to me. Great. So let's see what we can do with this if we control the accent level with the sequencer and tweak the tone and decay levels a bit. I'd say that we now have a perfectly fine hi-hat circuit, but there are 2 extra features that I'd like to add: a way to open the hi-hat and a way to control its pitch. Let's start with the former. In Roland 606 and 808 designs, they basically set up the open hi-hat as an additional voice, meaning that they introduced another trigger input and another envelope generator to get the job done. For our circuit, I don't think we need to go through all that, to be honest. Instead, I'd like to make our hi-hat's decay voltage controllable, so we can open the hi-hat by applying a voltage. Here's how that would work. If we add a PNP transistor between the envelope's resistance and ground, and then apply a voltage to its base, the capacitor cannot fully discharge, and so the hi-hat stays open. And the higher the base voltage, the louder the persistent sound. Since a real open hi-hat still decays in volume over time though, we'll want to introduce an alternate high-resistance path for our capacitor to discharge through. In my experiments, a 470K resistor worked well here, since it gave me a gentle drop in volume at the tail end of the open hi-hat sound. And here's how this sounds in practice. To trigger the open hat, I've connected the new CV input to my sequencer. I'd say it sounds a lot more organic with the resistor. Cool. Be aware that you need to ground the PNP's base if you're not currently applying a signal to it. Otherwise, the hi-hat is stuck in the open mode. Alright, so this leaves only the tune control, which is a little tricky because ideally we want to shift the frequencies of all 6 oscillators up or down by the same amount at the same time. Unfortunately, those frequencies are determined by the capacitor and resistor values in each individual oscillator core. So we'd have to find a way to manipulate all resistor or capacitor values at the same time, right? Lucky for us, there is an alternate hidden option: reducing the 4106 chip's supply voltage. That's because the upper and lower voltage thresholds that the chip sets internally to process the input depend on the supply voltage. If it drops, the thresholds move closer together. And if the thresholds move closer together, then we have to move less current through the resistor and into or out of the capacitor during each wave cycle to reach them, which should speed up the oscillation. Okay, but don't the inverter's output voltages also drop if the supply voltage drops? And wouldn't that cancel out the effect of moving those thresholds closer together? In theory, yes. If you look at the chip's datasheet, it claims that the relation between supply voltage, output voltage, and thresholds is always the same. But in practice, curiously, the thresholds move closer together faster than the output voltages drop. So let's try and exploit this. For that, we'll first set up a variable voltage divider. Because its output impedance varies wildly as we turn the potentiometer's knob, we'll then want to buffer it with an NPN transistor set up as an emitter follower. Next, we take the result and apply it to the 4106's positive supply pin. This way, the transistor will give the chip just enough current so that the supply voltage stays locked to the variable voltage divider's output. And here's how this pans out on the breadboard. As expected, turning the knob increases the pitches for all oscillators. Now, if we tweak this control in combination with the tone knob, we can get a bunch of different feeling hi-hat sounds out of our little circuit. But why stop at manual tune control? Since we're already using a voltage to set the oscillator frequencies, why not go the extra mile and also add a tune CV input? All we have to do to make that happen is somehow combine an external voltage with the one coming from our variable voltage divider before we buffer the result with our emitter follower. One slight issue though. Traditionally, you'd expect a tune CV input to increase the pitch as the input voltage goes up. But with our implementation, it would actually work the opposite way, since a higher supply voltage for the chip means lower pitch. To fix it, we'll simply subtract the control voltage from our manually set one, instead of adding it. This way, if the CV increases, the resulting voltage decreases, and the pitch rises. For that, we'll use a simple op-amp-based voltage subtractor. It does exactly what we're after. Subtract one voltage from the other and set its output to the resulting voltage. Before we send that voltage into the transistor's base, we need to take a pretty crucial protective measure though. Since we supply our op-amps with plus/minus 12 volts, the output can go negative if the CV is higher than the manually set voltage. And if the output goes too far below the 0 volts line, the transistor will break down and allow current to be pulled into the emitter, which could damage our 4106 chip. To prevent this, we'll simply insert a diode between the op-amp's output and the transistor's base, which will block any current from flowing in the reverse direction. Then, we add a 100K resistor to ground at the base to keep the node from floating when the diode is blocking. Let's test this by applying a slow LFO to the new tune CV input. Sounds like this is working fine. Next, I'll play with a manual tune control. While this does work in principle, we get some unexpected behavior towards the top end of the tuning range. The hi-hat goes almost completely silent. What's up with that? Simple. As soon as the 4106's supply voltage drops to 0 volts, the chip stops operating at all. In fact, the minimum supply voltage specified in the datasheet is 3 volts. So we need to make sure that we never drop it lower than that. How do we pull this off? Simple. By raising the pull-down voltage we set after the diode. Right now, it's fixed at 0 volts, but if we replace this 100K to ground with a voltage divider that produces round about 3 volts and connect the NPN's base to it, then the voltage at that node can never drop below those 3 volts. And that's because if the op-amp's output voltage tries to pull it lower, the diode will block. Great. There's one more adjustment I'd like to make though. As you probably noticed when I applied the LFO to the tune CV input, the hi-hat's pitch changed quite dramatically. In some situations, this might be what you want, but in others, you'd like to modulate the pitch in more subtle ways. To account for this, we'll add a simple variable attenuator to the tune CV input, allowing us to adjust the effect's intensity on the fly. And here's how this works out in practice. As expected, the hi-hat doesn't go silent anymore, no matter what happens in the tune section. Great. And with this, we've got a pretty feature-rich hi-hat circuit that can go from a thin and bright sizzle to a chunky white bark. If you try building this for yourself, let me know how it went in the comments. I'd also appreciate feature requests, improvement suggestions, or ideas for future videos. In case you're interested in supporting the channel, check out my Patreon page and the lineup of Eurorack DIY kits I develop in collaboration with Erica Synths. In addition to all my previous designs, this circuit is now available as a neat bundle containing a set of components, a PCB and panel, and an extensive write-up in the Erica Synths webshop. Links are in the description. Anyway, thanks for watching, and until next time. See ya!